Next, we will try to derive the Jacobian matrix, or we will try to see how do we define the Jacobian matrix. For doing that, first what is important is to understand how the velocity of an end effector is generally represented. Now, the velocity of an end effector, the velocity itself can be defined as into two different parts. The velocity itself can be of two types. First is the linear velocity. First is the linear velocity, and it is generally represented by v. The second is the angular velocity. Angular velocity is generally represented by omega. So let me write it. So the second one is angular velocity, which is represented as omega. What is the difference? One is a linear, the second one is based on an angle. To understand that, let us look at it one by one. First is linear velocity. In case of linear velocity, if we are going to take two positions at two different time that the end effector is going to be at. So suppose we are having first position at this point, which is represented by position x. Suppose I am just going to talk about one direction, and that direction is the x direction. In the x direction, I am suppose having one point x1 and another point x2, and my end effector is moving in this linear direction from x1 which at a time of t1 to x2 at a time of t2. Then generally the velocity is defined as x2 minus x1 divided by t2 minus t1. If I am going to take the difference of x2 minus x1 to be extremely small and the time difference also to be small, I can basically write it in its differential form as dx by dt. So if this is the direction x, then the velocity in x is basically given by dx by dt, and the direction is same, x. And this basically represents what is the speed or the velocity with which the end effector is moving in the x direction. This is only one dimension. In three dimension, we will have three different directions. We have directions which are basically x, y and z. Therefore, velocity in 3D space is represented by three different velocities in the x, y and z direction. So it's represented by a linear combination of dx by dt, dy by dt, and finally dz by dt. So this is the velocity, and sometimes it is also represented in certain textbooks as x dash, y dash, z dash, or even in certain textbooks as x dot, y dot, z dot. We will mostly try to follow this dot convention of this dot, x dot, y dot, z dot. That is what most of the textbooks are using. So we will also try to basically use that notation. So this is the linear velocity. The next one is angular velocity. The angular velocity basically happens when we are having the body or the end effector moving in an angular direction with respect to an axis. Here that is very important. Suppose we are having a point of origin is here, we are having two directions. One is in this direction, the second one is this one. Okay, let me use another ink. Okay, so suppose there are three directions here. One is going in this direction as I've drawn, the second is perpendicular to it, the third one is coming out of the paper. I have not drawn it because it is coming out of the paper. And suppose there is a link that is attaching from this origin up to this point, and here is the end effector. And this position can be represented basically by the angle theta 1. So I will say that the end effector is at position theta 1 at some time t1, and it moves to another position which is theta 2 angle at a time of t2. So basically I can say that theta 2 minus theta 1 by the time difference, which is dt2 minus t1, and that can be represented as d theta by dt. Okay, now what is important is what is the axis about which it is rotating. The axis is the one that is coming out. So if this is x, this is y, and the one coming outside is z, then the angular velocity omega z is basically represented by this d theta by dt. So the z is about the axis about which this is rotating. So if suppose we are having an axis like this and we are having a rotation about this axis, then if this direction is x, we will call the velocity, the angular velocity here, we will call it as omega x. If this is y, we will call it as omega y, and if it is z direction, we will call it as z. So what happens in 3 dimension? In 3 dimension, we are having whatever is the velocity. The velocity is a combination of, so I will write here in 3 dimension, the velocity, the angular velocity, sorry, the angular velocity is a combination of omega x, omega y, and omega z, sorry. And based on this only we will have, now whatever is the movement of the end effector, it is going to be always represented by, or it is represented as a linear motion or as an angular motion. So the end effector will have only these two motions. Now the motion that we are talking about here, because of which we will have a velocity, the velocity, as we told, we will have basically is because of the joint variable or the joints. So here if suppose there is a joint at z, the joint at z basically decides how fast this is going to move. Okay, so I can say that, let me put it this way, if an end effector moves with a velocity that is either velocity which is either linear or angular, it is because of the joint. It is because of the joint. So we can see that it's the joint velocity that leads to the end effector velocity. So I can say that therefore joint velocity results in end effector velocity. So end effector velocity. If that is the case, if that is the case, then the end effector velocity we can basically represent. We can represent the end effector velocity as a vector which has first a velocity in x direction, a velocity in y direction, and a velocity in z direction. Similarly, it may or may not have angular velocity, which is omega x, omega y, omega z, and that is related to I can first write that it is, since it is related to, I will first say that it is proportional to. So that is proportional to the the joint velocity. So we have already seen that joint variable is represented by q. So suppose we are having q1, q2, all the way up to qn. Now if you remember, let me just define. If you remember, we had said that if it's a prismatic joint, then it is going to be having a moment of d. If it's a revolute joint, it will have a angular moment of theta. Whatever is the linear moment, if I am trying to take the velocity of that, I will try to differentiate it. So it is d dot. Similarly, whatever is the movement, angular moment theta, if I am going to differentiate it, I will get the velocity. So this is the position, this is the velocity. Okay, so here we have said that joint velocity results in end effector velocity. So this is the end effector velocity that we have already written. So here we should write the joint velocity. So if any manipulator is having n number of joints, the joint velocity, that is q dot, q2 dot and qn dot, that is going to define the equation. So better I put it as smaller dots, otherwise. So dot dot dot, 3 dots. Okay, so it is q1 dot, q2 dot, qn dot, all the way. If suppose there are 6, then it is q1 q2 all the way up to q6 dot. If it's a 3 joint, then we'll just write q1 dot, q2 dot, q3 dot. So this is basically the relation which basically connects the end effector velocity with the joint velocity. Now this can be written as equation by putting the equal to sign. So I will write here, or I can write in another equation form. I can write it as that this relation is basically x dot, y dot, z dot, omega x, omega y, omega z. That is due to, so I have to remove the proportional sign, as you know that we have to put a value here. So that I am writing as some matrix J. Okay, and that matrix J has to be multiplied with whatever is left, which is q1 dot, q2 dot, all the way up to qn dot. Now when we define, we have to define what is the size of the matrix. So that is very important. So let me move this one a little bit side. This is a matrix which is having basically 6 rows and 1 column, and this is a matrix which is having n rows and 1 column. So what should be j, size of j, so that we get this answer as 6 cross 1. So as you know, matrix, this has to be of size 6 cross n. Then only we will have a relationship like this which will work. So that j should have a size of 6 by n. That j is called as the Jacobian matrix. So let me write here, j 6 cross n is basically called as a Jacobian matrix. Now we have to see how the Jacobian matrix will look for each and every case, based on, that is the section. This section is basically the derivation of the Jacobian matrix. We have just defined. So we have just defined the Jacobian matrix. Now we have to put for each and every case, and we have to slowly find out what the structure or what the equation of the Jacobian matrix will be like, or what this whole equation will look like. And then we will go to individual cases of different kind of manipulator and try to define the Jacobian matrix. So I will stop here. And I will first define mathematically how do we write the velocity, and how do we connect it with q1, q2, and so on, so that we are able to define the Jacobian matrix in a much easier manner. Thank you.